A set is a collection of objects viewed as a single entity. C'est tout ce que c'est. I have some objects. I decide to look at them together as one thing. That collection is a set. The objects inside the collection are called elements or members. They belong to the set. The set contains them. If I have a bag and I put 7 marbles inside, the bag is the set. The marbles are the elements. Except in mathematics, the bag can hold numbers, points, functions, curves, or objects of any kind whatsoever. I'll use capital letters for sets, A, B, C, and so on, and lowercase letters for elements, A, B, C, X, Y, Z. If an element X is inside a set S, I write X in S using the symbol that looks like a curved E. If X is not in S, I write X not in S with a line through that symbol. I can describe a set by listing its elements inside curly braces. The set of positive even integers less than 10 is written as the collection containing 2, 4, 6, and 8. If I want to describe a set by a property instead, I write S equals the collection of all X such that X satisfies some property P. The colon reads as such that. From a given set, I can form new sets called subsets. The even integers less than 10 that are also divisible by 4, those are 4 and 8. That smaller collection is a subset of the larger collection containing 2, 4, 6, and 8. In general, a set A is a subset of B, written A is contained in B, whenever every element of A also belongs to B. The statement A is contained in B does not rule out the possibility that B is also contained in A. If both hold simultaneously, every element of A is in B and every element of B is in A, then A and B have exactly the same elements, and I call them equal. I write A equals B. If A is contained in B but A does not equal B, I say A is a proper subset of B. The inner cylinder is the set A. It contains 4 green elements, 1, 2, 3, and 4. The outer cylinder is the set B. Everything inside A is also inside B, because A sits entirely within B. A is a proper subset of B because every element of A belongs to B, yet B has elements that A does not. I also need one more set, and honestly, this one confused me the first time I saw it. I need a set that contains nothing at all, no elements whatsoever. I call it the empty set, and I write it with the symbol that looks like a 0 with a line through it. I agree to call the empty set a subset of every set. If I think of a set as a box containing certain objects, the empty set is an empty box. It belongs inside every other box by convention because the statement, every element of the empty set is in B, is automatically true. There are no elements to violate it. Mathematicians call this a vacuously true statement. There is no counterexample because there is nothing there at all. Now I need to talk about pairs where the order matters. If I have 2 elements A and B, the set containing A and B is written with curly braces, the collection of A and B. By the definition of set equality, this is the same as the collection of B and A. The order does not matter. Curly braces say, I have these things, not, I have them in this arrangement. But sometimes order does matter. In coordinate geometry, the point at position 3, 4 is different from the point at position 4, 3. the pair is ordered. To express this, I use parentheses instead of curly braces. The ordered pair AB. Here, A is the first element and B is the second, and that distinction is permanent. There is a purely set-theoretic definition of the ordered pair, due to Kuratowski. It states that the ordered pair AB equals the set containing two elements, the set whose only member is A, and the set whose members are A and B together. Written out, AB equals the collection containing the singleton of A and the pair of A and B. I remember finding this definition strange the first time I saw it. It looks like an odd encoding, but it works because it satisfies the one property I actually need. Two ordered pairs, AB and CD, are equal if and only if A equals C and B equals D. The first element is genuinely distinguished from the second. That is theorem 2.2 in Apostol, and proving it is a good exercise in applying the definition of set equality carefully. Given two sets A and B, I can form a new set by taking every possible ordered pair where the first element comes from A and the second comes from B. This new set is called the Cartesian product of A and B, written A cross B. I can see it spatially. If A is a set of points along a horizontal line, and B is a set of points along a vertical line, then A cross B fills out a region in the plane. Every point in that region has a horizontal coordinate from A and a vertical coordinate from B. The most important example, if R denotes the set of all real numbers, then R cross R is the set of all ordered pairs of real numbers. That is the coordinate plane. And Apostol notes that R cross R can also be thought of as the set of all complex numbers, since every complex number is determined by an ordered pair of reals, its real part and its imaginary part. Now I reach one of what I consider one of the most important ideas in all of mathematics, the concept of a function. But I want to approach it carefully, because there is a more general idea that comes first. Suppose I take ordered pairs of real numbers, x, y, and consider expressions like x times y equals 1, or x squared plus y squared equals 1, or x squared plus y squared is less than or equal to 1, or x is less than y. Each of these expressions defines a certain set of ordered pairs, the pairs for which the expression is satisfied. I can plot those pairs as points in the plane. The equation x times y equals 1 gives me a hyperbola. The equation x squared plus y squared equals 1 gives me a circle. The inequality x squared plus y squared less than or equal to 1 gives me a filled disk. The inequality x less than y gives me everything above the diagonal line. Each of these is a set of ordered pairs, and each of those sets is called a relation. Formally, any set of ordered pairs is a relation. If S is a relation, the set of all first elements x from the pairs x, y in S is called the domain of S. The set of all second elements y is called the range of S. I can think of the domain as what goes in, and the range as what comes out. A function is a special kind of relation. A function f is a set of ordered pairs x, y with one additional rule. No two pairs have the same first element. In other words, if x, y is in f and x, z is in f, then y must equal z. For every input x in the domain, there is exactly one output y. I usually write y equals f of x instead of writing the pair xy is in f. The notation f of x means the value that f assigns to x. Two functions f and g are equal if and only if they have the same domain and f of x equals g of x for every x in that domain. This is theorem 2.6. For every input x in the domain, there is exactly one output y. A function is completely determined by what it does to each input, nothing more, nothing less. When the domain of f is a subset of the real numbers, I call f a function of one real variable. When the domain is a subset of the complex numbers, I call f a function of a complex variable. When the domain is a subset of a Cartesian product a cross b, I call f a function of two variables, and I write f of a comma b instead of f of open parenthesis a comma b close parenthesis to keep the notation clean. If S is a subset of the domain of f, I say f is defined on S. The set of all values f of x for x in S is called the image of S under f, written f of S. If T is any set that contains f of S, then f is also called a mapping from S to T, written f from S to T. If f of S equals T exactly, every element of T is actually hit, then the mapping is said to be on to T. A mapping from S into itself is sometimes called a transformation. I can visualize this with a concrete example. Take the function of a complex variable defined by f of z equals z squared. If I take a sector of the complex plane, say all z whose angle from the positive real axis is between 0 and some angle alpha, where alpha is at most 90 degrees, then f maps that sector to a new sector whose angle ranges from 0 to 2 times alpha. The squaring function doubles the angular spread. A thin wedge gets stretched into a wider wedge. If two functions f and g satisfy the relation that g is contained in f as a set of ordered pairs, I say g is a restriction of f. Or equivalently, f is an extension of g. If I take a function f defined on a large domain and I only look at what it does on a smaller set S, I get the restriction of f to S. The restriction consists of those pairs x, f of x, where x belongs to S. I need a particular type of function that will matter enormously in analysis. A function f is called one-to-one on S if it sends distinct inputs to distinct outputs. Formally, whenever f of x equals f of y, I can conclude x equals y. Different inputs always produce different outputs. Another name for this property is injective. One-to-one functions matter because they have inverses. But before I define the inverse of a function, I need the more general idea of the converse of a relation. Given a relation S, the converse of S, written with a breve accent over S, is the set of all pairs AB such that the reversed pair BA belongs to S. I just swap the elements in every pair. If S is a relation in the plane, the converse is the reflection of S across the diagonal line y equals x. Now, if a function f has a converse that also happens to be a function, that converse is called the inverse of f, written f inverse. Not every function has an inverse. If f sends two different inputs to the same output, the converse will try to send that output to two different values, which violates the definition of a function. I can think of it graphically. If I draw the graph of f and it passes the horizontal line test, meaning every horizontal line hits the graph at most once, then the reflection across y equals x will also be a function. If f fails the horizontal line test, the reflection will not pass the vertical line test, and there is no inverse. Theorem 210 states the exact result. If f is one-to-one on its domain, then the converse of f is also a function. The proof is straightforward. If the converse sends x to y and also sends x to z, that means f sends y to x and f sends z to x. So f of y equals f of z. Since f is one-to-one, y must equal z. The converse never assigns two different values to the same input, so it is a function. I can combine functions. Given two functions f and g, where the range of f is contained in the domain of g, I form the composite function g composed with f, defined by g composed with f of x equals g of f of x. I first apply f, then apply g to the result. Composition is not commutative in general. G composed with f and f composed with g can be entirely different functions, and f composed with g might not even be defined if the range of g does not sit inside the domain of f. But composition is associative. H composed with g composed with f equals h composed with g composed with f, whenever both sides make sense. Among the most important examples of functions are those defined on subsets of the integers. These are called sequences. A finite sequence of n terms is a function f, whose domain is the set containing 1, 2, up through n. Its range is written as f sub 1, f sub 2 through f sub n, and the values are called the terms of the sequence. An infinite sequence is a function whose domain is the set of all positive integers, 1, 2, 3, and so on without end. The range is written f sub 1, f sub 2, f sub 3, continuing forever, and f sub n is called the nth term. I write the sequence whose nth term is f sub n, using the curly brace notation with a subscript n. Now I can define something important, a subsequence. I start with an infinite sequence S, and I pick out certain terms, but I have to pick them in order. Formally, I have a function k from the positive integers to the positive integers that is order-preserving, meaning k of m is less than k of n whenever m is less than n. The composite function s, composed with k, gives me a subsequence. Its nth term is s sub k of n. A concrete example makes this clear. Let S be the sequence whose nth term is 1 over n. Let k of n equal 2 to the power n. Then the subsequence has nth term equal to 1 over 2 to the n. The values 1/2, 1/4, 1/8, 1/16, and so on. I picked out every term at a power of 2 position. Two sets A and B are called similar or equinumerous if there exists a one-to-one function whose domain is A and whose range is B. I write A is similar to B. This function establishes a one-to-one correspondence between the two sets. Every element in A is matched with exactly one element in B, and every element in B is matched with exactly one element in A. Every set is similar to itself. I just use the identity function. If A is similar to B, then B is similar to A. I just use the inverse function. If A is similar to B and B is similar to C, then A is similar to C. I compose the two functions. These three properties mean that similarity is an equivalence relation on sets. It tells me that two sets have the same size in an exact sense. Let me pause here and look back at what we have built together. We started with something very simple, a collection of objects, a set, analogous to a bag with things inside it. If that felt too simple to have even talked about, I hope you can see now that it was the foundation of everything. From that single idea, we started building on it little by little. We took elements and grouped them into subsets. We met the empty set, a container with nothing inside which somehow belongs every set. We defined what it means for two sets to be equal. They contain exactly the same elements. Then we talked about order. A set does not care about arrangement, but some aspects of mathematics often does. So we built the ordered pair, a construction where first and second are permanently distinguished. And from ordered pairs, we built the Cartesian product, every possible pairing of elements from two sets. With ordered pairs in hand, we defined relations, any collection of pairs. And from relations, we carved out what I consider one of the most important ideas in mathematics, the function. A relation where every input produces exactly one output. One question, one answer. If that definition felt rigid, it was meant to be. That rigidity is what makes functions in quotes trustworthy. We studied what functions can do. We defined the image of a set under a function, where the arrows land. We defined mappings, onto mappings, and transformations. We defined restriction and extension, shrinking or growing a function's reach. Then we asked a deeper question. When does a function preserve distinctness? That gave us the one-to-one property, injective functions, where different inputs always produce different outputs. These are the functions that can be reversed, and reversing led us to the converse of a relation and the inverse of a function. We learned to combine functions through composition, feeding the output of one into the input of another. Composition is not commutative, but it is associative. We define sequences as functions on the integers, and subsequences as compositions with order-preserving selectors. And finally, we used one-to-one correspondences to compare the sizes of sets. Two sets are similar when we can match their elements perfectly, with nothing left over on either side. Similarity is reflexive, symmetric, and transitive, an equivalence relation. It gives us a precise way to say two sets have the same size. If any of these ideas felt abstract or difficult, that is completely normal. These are ideas that took the greatest mathematicians generations to formalize. The fact that you followed them here means you are on to something too. This is our vocabulary now. Sets, functions, sequences, similarity. Every definition built from ordered pairs. Every theorem proved by checking what the definitions actually say. In part 2, we will use this vocabulary to ask a question that shook mathematics when it was first answered. Can an infinite set be the same size as one of its own proper subsets? The answer is yes, and that single fact separates the finite from the infinite, the countable from the uncountable, and opens the door to the deepest ideas in analysis. The language is set. The real work begins next. Thanks for watching. See you there.